So far, we have taken a look at the various options available for API being the mode of serving for the machine learning models. Uh, Next up, we will take a look at what are the ways in which you can serve the models themselves without requiring an API to wrap it up. So if you take a model directly, what are the options for wrapping the model itself in such a way that you can start serving the predictions from it? There are fundamentally two types. One, you take the model and you wrap it up in batch code, or you take the model and you wrap it up in streaming code. A batch code would be an example of a batch Python program that you execute, within which the model itself is called as one of the steps. Likewise, in a streaming code, it's similar, meaning that there is a bunch of code that does a lot of things, and one of the code elements is basically the model invocation. So the example of a batch Python program is similar to the unit testing that we did as part of the CI setup for the first time in CML. So that's a good example because it's just a Python program that read a joblib file and then executed it. Whereas in the streaming code, you would need to work with specific streaming libraries, like for instance, the combination of Spark streaming with Kafka, and then within that streaming library, you would then execute the model code and use that for streaming predictions. So details about the streaming code implementation of how models get invoked is too advanced for this course, and it's not directly related to the objectives of this course. But if in case you're serious or want to learn about it in a much more detailed manner, there is the separate course that I host, which is called the Introduction to Big Data, and that can be a very good vehicle for you to learn more about this. So what is batch inference? It's for processing large data sets where the model needs to be executed on those data sets either at once or periodically. So the use case here would be something like a churn prediction. We don't want to predict churn for a business on a daily basis, which doesn't make sense for some of these businesses, or real time for that matter. It's good enough that we execute it once a week or once a month. The other example is, for instance, we've got a bunch of users who are historical users of our website or a platform or service, and we want to just occasionally weed out the fraudsters. So we run this once in 3 months as a process. So in this kind of setup, you've got to have few associated tools on which the model depends, a model execution depends. First, of course, is the data pipeline, which is used to process this batch data, and that's typically if it's large data, then it'll be Spark, or if it's small enough data, then it's just a regular pandas kind of a data processing in Python. Since you'll need to run this periodically, you'll need some kind of a scheduler, like what's called one of the open source schedulers is called as Airflow. And then last but not the least, you would need the model joblib itself as a file, a pickle file, right? And invoke that as the model that you want to load and execute against the batch data. So that's batch inference. In streaming inference, you're doing something similar to batch inference, but now you're doing it on every data element as and when it arrives. So you're not waiting for large amounts of data to get collected. You might still wait for a small window of data to get collected, which might have like one or more data elements or data records, but you're not waiting for long periods of time. So here the use case is going to be more around real-time fraud detection or live recommendations for a user who's logged into the website at a particular point in time. So it might not use APIs, but it might use the model itself directly, but it uses it in a streaming fashion. So you're not waiting for data to get accumulated in any way. You're operating on the data as soon as it arrives. So here the tooling is vastly different. You would need the right set of tools to collect the data in a single place and also make the data available as and when it arrives. So Kafka is a great technology for this. Spark streaming is what one of the examples of software which can be used to read data from the Kafka and operate on it instantaneously, along with, of course, the model code itself, which can get called as a joblib file or a pickle file, or in some cases, you can also instantiate there as an API internally and have that API be called within Spark Streaming. So that's the streaming inference model. Now, so far we've spoken about serving options. Let's talk about deployment options, right? Before we talk about deployment options, we need to understand where can the models be deployed, either as APIs or as models themselves. First up, local, of course, because that's where the developer operates fundamentally. They use the local machine for development. But realistically, it's not meant for anything more than that, right? You can't use the local machine for production. The second deployment area that's possible is edge. Edge means you deploy the model at the mobile device, at the edge of the typical company network, right? So we'll see more examples of this. The third deployment area could be production grade servers, like the Kubernetes cluster that we just did a demo for. That's on public cloud, which is Google Cloud. Or these production grade servers can be in the data centers within a company, or it could be in private cloud, which is owned by each company by itself. And last but not the least is truly serverless options which exist on the public cloud. So let's take a look at each of these. Edge deployments are when the models get deployed onto a mobile device, like for instance, the Siri that's there in my Apple phone, the Google Gemini that's there in your Google Android phones, etc. Right? That's a mobile device edge model or edge AI, or it could be embedded devices, like for instance, a standalone smart refrigerator or a standalone smart camera, right? That's recording me at this stage. So in those kinds of systems, you need additional software which allows you to work with the model that you've deployed. So for instance, for mobile-based inferencing, TensorFlow ships with a version of itself which is conducive for mobile-based executions, which is called as TensorFlow Lite. The key difference between TensorFlow Lite, or even any other edge AI software is that you need to work with much lesser number of resources. Like for instance, you won't have access to a GPU potentially. You might need to work with compressed models, etc. So TensorFlow Lite, Core ML are two such libraries which can be useful. For embedded systems, you might need to recompile from the get-go, right? Which is where you might use GPU compatible frameworks which NVIDIA provides, called as Jetson. So edge AI is basically meant for low latency predictions, where you want the predictions to happen at the point of source of origin of data, right? Source of data. So for instance, if you look at the way we use voice assistants on our mobile phone, if for instance we assume that every single time the voice assistant has to talk to a central server to relay our request and then come back with an instruction, etc., it just takes that much longer, right? Because each time it talks to a central server, it's orders of couple of seconds latency, because it has to go through the network, the public internet, and then it comes back with a response, and then we ask it to refine, blah blah blah, right? All of that takes time. All of that takes much longer latencies than what is possible and what the user experience can afford. So offline is the other angle here. I should be able to operate Siri on my phone without my phone requiring internet access. How is that possible? How much intelligence can be embedded within it? So those are the considerations that typically arise when we talk about edge deployment options. Serverless deployment, on the other hand, is speaking about ways in which you can, deploy models on public cloud, right? In a way that you don't have to worry about the infrastructure at all. So let's go back to, Vertex AI that we initially started this entire course with. Vertex AI, we took a look at one particular feature it has, which is Workbench. And within Workbench, we made it create an instance, and within that instance, we put a notebook. But if you look at Vertex AI's options, the rest of it, it's got a lot of options for other things as well that we've talked about in this course, which is being able to run a notebook without creating an instance, being able to work with models directly without having to, create APIs, being able to have experiment tracking, just like MLflow did, model registries, just like MLflow did, ability to create artifacts. We used it, in fact, in the demo we did with Kubernetes. And it's got integrations with Kubernetes as well. So Vertex AI actually is an example of a public cloud ML platform which goes the whole 9 yards of what is required for a machine learning model to be developed all the way till when it's productionized. So in this in this use of Vertex AI as a feature, as a platform, you can think of it as a serverless platform, or a platform as a service. That's the right precise term to use, which simplifies the need for you to understand a lot of the infrastructure details or the automation details, right? So that's one approach, which is a platform as a service approach. The next approach is where you go completely serverless, which means you use options which absolutely do not require you to think about the hardware at all. So contrast this with the Kubernetes demo. There we had to provision a cluster. While we used the default settings for the cluster, which means there were default number of nodes, pods, locations or regions where the cluster was deployed. If we wanted to, or if we wanted our own flexibility, we would have chosen all of those specifics ourselves, like including node types, etc. So that's one way of going about deploying machine learning models. In a true serverless setting, on GCP, for instance, that service would be called as Cloud Run. We wouldn't even worry about creating a cluster. In those kinds of services like Cloud Run, it would provide completely serverless container execution. All we would need is just the image, and Cloud Run would automatically spin up the nodes, automatically scale up or down based on the current usage, etc. Encourage you to try it out. We're not going to get time to try out Cloud Run in its entirety as part of this course, but spend a few more extra credits. Just try out Cloud Run, contrast that with Kubernetes. You'll see the difference between serverless deployments versus managed, server deployments. Okay, so let's now start putting together what the CD pipeline looks like. And in fact, what we're going to discuss here, the CD pipeline in this slide, is going to be your homework, right? While we continue to use Iris as the base data set, the Iris classifier problem statement as the base problem statement, for this week's assignment, you would actually do the build out of the CD pipeline with CML. So please pay attention to this slide. What we want to be able to do with a continuous deployment pipeline is to have automation around 3 important steps. The first is take the app that we have done, which is basically the model that we have trained, and this is basically the output of the model that's already been tested out using CI, right? It's already been validated using staging data, validated data, whatever. So that app you containerize using Docker. We saw how using the Docker demo. You run tests on top of this Docker container to ensure that it's producing the results that you wanted to produce, at the minimum some sanity tests, right, on prediction. And then you go deploy this on appropriate Kubernetes clusters via container or artifact registry, like what we did with the Kubernetes demo. Here the keyword appropriate refers to the environments, right? Like for instance, in Kubernetes, especially in GKE, there is no concept of a staging environment or a prod environment. That's just nomenclature or jargon or segregation of space that we as a company, as a best practice follower, want to follow, right? So when you create a cluster in GKE, you can give it a tag which says this is a staging Kubernetes cluster, and therefore it has limitations with respect to how much it can scale, or how much data you wanted to process, or how long you wanted to live for. And then production Kubernetes cluster is separate. It's altogether a different cluster with a different tag, with a different time to live, etc., etc. So that's what appropriate refers to here. So a typical CD pipeline will basically automate these 3 steps and get it to a stage where the model is deployed on a particular Kubernetes cluster. So please do this on your account as the homework for this week. Let's put this all together. Whatever we have learned so far, we're going to use Git-flow as the pattern of choice. We're going to use deploy code as the lifecycle pattern of how we would productionize machine learning code. We will work with GitHub as the code repo, GCP as our platform for deploying and executing code, CML and MLflow as tools for specific aspects of the MLOps best practices. So with all of this, we'll productionize machine learning models now, right? So let's go through it step by step. First and foremost, you've got CI. Okay, even before CI starts, firstly, there is a feature branch, right? By adopting Git-flow principles, we would create a separate feature branch or a separate model branch for a new model that we want to create for a problem statement. So in that branch, we would do lots of different check-ins and commits based on all the different things that we are developing. So when we are ready to do a merge with the develop branch, we raise a pull request. Or alternatively, for every commit that we do to the feature branch, we raise a we do testing. So in either of those scenarios, there would be a CI that will be required, which is continuous integration, which runs a bunch of unit tests, which runs sanity tests, and then provides that as an output in a comment in that particular GitHub repo. Somebody is now going to go take a look at that comment, take a look at the CI tests to see whether it passed and whatnot. So let's assume, for instance, that this is a PR, a pull request into the develop branch that's happening. So then the manual check that happens in GitHub for this PR will ratify, and let's say it approves, which means then it will go ahead and merge that feature branch or new model branch with the develop branch. As soon as that merging is done, as part of the automation that you would have written in the homework pipeline as well, the CD pipeline will run, which means that CD pipeline will produce a model which is deployed in the staging environments Kubernetes cluster, which means it's the staging Kubernetes cluster. As soon as that is done, then there would be an automated step that needs to run, which will provide that staging Kubernetes cluster with the staging data or staging workload, which will then execute the staging workload and verify the outputs, right? Once that is done, then there would be a PR that is raised to merge that develop branch code into the main branch or into the release branch, as the case may be. At that stage, there would be another CI that's done because the main branch, the release branch, might have deviated from the develop branch at some point in the past. So therefore, a fresh round of testing. That CI has its own set of tests, by the way, right? Not necessarily it's a copy of the CI that's there in step 1. And at that stage also, CML will help it create a particular comment along with the report for accuracy, etc., etc. So there is a manual approval for that step. That manual approval will then ratify and then say it's okay to merge with main or merge with release. And then that will in turn trigger the CD pipeline for that merging, right? As soon as the merge is done, the CD pipeline gets triggered and then the model gets deployed in production Kubernetes cluster automatically. Notice that there is no human involvement in touching the production environment, right? So the CD pipeline automatically deploys that. The CD pipeline deploying that also would have registered that model in MLflow. So therefore, you are now ready to have the challenger model, because that's the new model that you've deployed right now, compete against the champion model. How much of the competition happens? How do you split the traffic? All of that corresponds to the load balancer configuration of that Kubernetes cluster. In fact, you can have another load balancer which sits as a separate service, which then routes the traffic to the load balancer of the new Kubernetes cluster that you've created now for the new model, the challenger model, and routes the remaining traffic to the champion model's Kubernetes cluster's load balancer. So that happens as a parent load balancer configuration. So that comes down to the functionality that you have already deployed. So then You go through this champion challenger evaluation, and then let's say the results are out after a week or a month, right? At which point there's manual review. The manual review finds that the challenger is actually doing really well, and it's time to promote. How do you promote? At that stage, go to MLflow, promote that model as the new champion model, and from that point on, the load balancer traffic can be completely rerouted to the challenger model's production Kubernetes cluster, and then the champion model gets sunset, and in MLflow, the champion model gets archived. So that's your complete CI/CD pipeline for ML in production for enterprise grade governance and observability. Thank you, and we'll see you in the next week's course where we'll start talking about monitoring.